This question is about the speed of sound in the water. So we are given these two graphs. The first graph shows how the speed changes with depth, and the second graph it shows how the depth of that sound wave changes with the distance from the source, right? So just to understand what is actually happening here. So the information we get from the first graph is that 900 meters, 900 meters is where the sound is produced, and then it starts traveling towards the surface. So therefore, the depth we're gonna get less. So from 900, it will end up to 800 and 700 and so on, right? But then you can see from the second diagram that even though it's traveling to the surface at 700 meters depth, it changes direction and it's going deeper again. Now, in order to understand what is really happening here, we need to kind of break it down a bit. Firstly, we know that if a wave is moving from a more dense to a less dense medium, what is happening? We have refraction, and therefore it's moving from more dense to less dense, therefore it's going to move away from the normal. Now, what does more dense and less dense means? It means that in terms of velocity, it means that when it's in a more dense material, it is moving slower, and then when it's going to a less dense material, it's moving faster. This change in speed, right, the fact that it's changing medium and it's going faster, it's causing the change in direction. Now, if we look at what's happening here, let's see, we have the three areas, 1, 2, 3 areas. So the first one is when the water is at around 900 meters, and based on the graph, if I check at the 900, I see what is the speed. It's around 1,477 meters per second. Then when the wave goes into 800 meters, again from the graph that we see that the speed increases slightly, which is around that. And if it goes to 700, again it increases even more, which is around 1,479. So I'm just drawing this so you can understand what is actually happening. Now, the sound goes from 900 to 800. Even though it doesn't change medium, the fact that it's changing speed for any reason, it's going to cause it to change direction. As we said before, change in speed is resulting in changing of direction. So where is this going to go now? It's going to go away from the normal. So it's going to start moving away. Yeah, so imagine this is keep happening every time the speed changes slightly, the wave is moving away from the normal. Now, at this point over here on the second diagram, we can see that when it reaches 700 meters, it's changing direction and it starts going deeper again. So what do you think happened in that case? In that case, apparently we don't have refraction anymore, but we have total internal reflection. And when does the total internal reflection happen? It happens when the angle of incidence is greater than the critical angle in that boundary. So, and it looks like this is exactly what happened, right? This is why the sound has changed direction, and from moving up the surface, it started going deeper again. So the first question is asking us to explain why the sound follows the path that is shown on diagram B. I have copied the graphs here so we can refer to them straight away. So, and what I have discussed is what is actually this is what we need to answer here. So now I'm just gonna write a bullet point just to save some time. So why it's moving like that? First, as I explained before, the sound from 900 meters depth, when it's moving upwards to the surface, that means going to 800 and 700, it's speeding up. So wave speeds up as it moves from 900 to 700 meters depth. And every time it changes speed, it's changing direction as well. Yeah, and you can see that it's slowly changing direction, because as you can see here from the values that we have used before, the change in the speed, it's tiny. So the changes in direction will be tiny as well. That's why we have this kind of smooth curve in terms of changing direction. If we had a huge jump, if we had a huge change in speed, then the direction will change more rapidly as well, right? So, and this is what's happening when it goes from air to glass or air to water, when we have a huge change in speed. In that case, because the change in speed is tiny, then the direction will also change very smoothly. All right, so then we say that no sudden change in speed, therefore no sudden change in the direction as well. Okay, and what is happening every time it changes speed? The wave is refracted, and because the speed increases, is refracted away from the normal. So the wave is refracted and is refracted away from the normal, as we have explained on the diagram above. And what happens at the boundary when it goes to the 700? As we said again, the angle of incident apparently is greater than the critical angle, therefore we're going to have total internal reflection. So at 700 meters, angle of incident is greater than the critical angle. Yep, therefore at 700 meters we're going to have total. We don't know if it's total actually, so but most of the wave, most of the sound, internal reflection, right? So it's reflection that we have, it can be total internal reflection. These will be the 5 points for this question. Then B, sound that travels in a straight line from the source to point B takes longer to arrive than sound that travels along the path shown in diagram B. So what is actually telling us here is that if another sound, another wave was traveling directly from the point that was produced into point B, which is on the same depth, even though the red line is a shorter distance, it's taking longer to reach there. So that wave that follows that path, it's actually going faster. So why is this happening? So the explanation is on the previous graph. If something is moving at the depth of 900, it will keep the same speed, which is that, let's say. But the fact that the sound that's following that path is going into shallow waters, not shallow, I mean less depth, you can see that the speed is actually higher. So even though it's covering more distance, the fact that it's traveling at a higher speed it will allow that sound, that wave, to reach point P faster than going straight from the 900 straight to P. So for B, we can say that even though path B is longer, the sound wave travels faster on the path on diagram B. Here is not the path B, even though, oh yeah, that's what I was correct, sorry. So even though the path B is longer, the sound wave travels faster on that path. So it reaches faster than going straight. And C suggests two factors that might cause the speed of sound to vary with the depth of the sea. Just a reminder, I'm using this diagram as a reminder, right? Sound is a longitudinal wave. Longitudinal waves, they need medium. And the way that the wave travels, the way that this energy travels is that the particles, something causes a vibration of these particles, that will be the source of the sound. And these particles, they start to vibrate parallel to the direction of the sound wave. So one particle will hit another one, and then this kind of oscillation, this disturbance will start traveling as well. Right? Now, what will make this oscillation, let's say, to move faster? What will make this wave to move faster? Looking at the diagram, you can say that if the density of the water is higher, how is that going to change? So higher density means more particles. More particles, easier for the sound to travel. So density of the seawater will affect. And also, if the temperature will be higher, that will also affect that, because if the temperature is higher, these particles, they will have more energy. Therefore, the wave, they're going to oscillate even more, and then the wave will actually propagate faster. So that will be temperature of the water. And last one, we can also say about the pressure. Right, pressure is linked to the force that applies, and of course to the energy that the particles have. So any two of these three will actually cause the speed of sound to change.